Okay, so let's take a look at the dynamics of these two solutions that we looked at on the previous slide a little more carefully. So I want to kind of blow up that little phase plane picture that we started drawing on the previous slide. So we're working with the same system of differential equations. We've found the general solution prior, and what we observed on the previous slide was that this solution that starts off at 3, 0 over here is special because if I start off on this point, I'm going to always remain on the line y equals 0. So the solution that starts on this line is going to stay on this line. And moreover, we notice that if time goes on, that there's a direction to this solution that it heads to the right. So as time went to infinity, we saw that x was going to get infinitely large, y was going to remain 0. If instead we were to start with a negative value of x, what you would similarly see is that as time goes to infinity, that value for x is going to head to the left. It's going to get more and more negative. So what we can see here is that solutions that start on the x-axis are going to stay on the x-axis, and in fact, they're going to move away from the origin. Let me just note that. And it's worth noting here that the origin is special because it's our equilibrium solution, right? It's the only solution if we were to start off with x equal to 0 and y equal to 0, that solution would remain constant. So solutions on the line y equals 0, they move away from our equilibrium at the origin. Whereas solutions that start at the point 2 minus 1 or any other point on this line in blue are going to, first of all, they're going to stay on that line since the ratio of y to x remains constant. And as time goes to infinity, these solutions, since the power in x, the power of the exponential part is negative, as time goes to infinity, those solutions head in towards the equilibrium. So I'm just going to write that those solutions head towards the equilibrium at 0, 0. And similar to null-Kleins, here we have a couple of really special lines in the phase plane where I know that a solution that starts on this line is going to stay on that line. And that's going to allow us to fill out the rest of the phase plane. So for example, if our initial condition was at 1, 1, and I would be someplace over here, for example, in the first quadrant, then these arrows are going to tell me what direction I need to move in. So this solution is going to head off in this direction. So it's going to move down and to the left as time goes on. Excuse me, down and to the right as time goes on. And if we started off at a point like 1 minus 1, say over here, I can see here that this solution is going to head this way, and then it's going to head out this way over here. So we can see what these solutions look like over here. And we can pick solutions in other areas. If I were to start at a point, say this point in red over here, I can see that this solution is going to move this way. So we need to stay within these important lines that I drew in blue and black. And this solution, if I were to start over in this region, I can get this little solution in red over here. So similar to how we could fill out the phase plane with all sorts of solutions based on how we knew the null-Kleins were lined up, we can use these really special solutions that remain on straight lines to fill out the phase plane to describe how where given any initial condition, what's going to happen as time goes on. Okay, so I want to just show you what this looks like using a little applet that I put a link onto Canvas. So I'm just going to make a short little video that illustrates how you could use that applet, because I think that's going to be a nice tool for you guys to use as we work through this section in terms of picturing the dynamics of the phase plane and how that relates to some of the special solutions that we'll take a look at.